Good morning, everyone, and welcome to our webinar today on methods for modeling nonlinear relationships. It's my pleasure to introduce Ruth Croxford, who will be our presenter for today. Ruth is a senior epidemiologist at ICES. She has a master's degree in statistics from the University of Toronto and in computer science from Queen's University. And she said she will try not to embarrass any of these institutions during this webinar. I'm sure that she will absolutely not be doing that. At ICES, she has contributed to the design and analysis of projects covering a wide variety of topics in healthcare. In the process, she's been extremely fortunate to continually learn from colleagues and researchers. She is pleased to participate in this webinar series. We're happy to have her, and I know that you'll find lots of valuable information from her presentation today. So without further ado, I'll pass it over to Ruth, and if you have any questions along the way, please let me know. Thanks, Ruth.
Thanks so much, Anne, and hi, everybody. Welcome to the webinar, where we're going to discuss various ways to deal with continuous predictors in regression analyses. We're going to focus on deciding whether a continuous predictor has a linear relationship with the outcome, and if it doesn't, how can we find out what the best shape of the relationship is? Hopefully, I've left some room in the presentation for a short break around the middle, and also some time for some questions. Now, Anne wanted me to show myself on camera, and I said, well, that just wasn't going to happen. But here's a picture of me, that's me in the middle, taken in January before we knew what was coming down the tubes for all of us. This was taken at an Argentinian research station in the Antarctic, on a trip to the Antarctic. And on your left, on the left of the screen, is my wonderful cabin mate who's from New York City, so she's not had a very good time of this COVID epidemic. Well, that was 4 short months ago, and this is sort of what things look like today. Okay, so our goal is to create a regression model which captures the relationship between a continuous predictor, or maybe you have more than one, and some outcome. I'm going to do an overview of the various choices that we have for including continuous predictors in regression models, with a focus towards the end on 2 techniques, restricted cubic splines and fractional polynomials. I've got a couple of disclaimers because I'm from ICES. I have to say that the data that's going to be used here, unless it's really obvious that it's coming from a manuscript, a published manuscript, the data that's going to be presented is fake. It was produced using simulation. And please don't leave this webinar thinking that you've learned anything in particular about healthcare. And this is my second disclaimer, which I like to put up for my presentations, which is that the webinar is going to take more than 10 seconds, and I'll let you decide whether it's worth it or not when we get to the end. Well, my overview was very easy to put together because it's found in this table, which is taken from a book called Clinical Prediction Models. You can see the reference at the bottom by Ewout Steyerberg. It's a great book. And this table is adapted from the book. And somebody asked, what do I mean by adapted? And what I mean is these are basically his words. I had to squish a few words down to get it to fit in a PowerPoint slide, but this is basically what it says in his book. I'm going to cover each of these methods, as I said, with a concentration on the 2 at the bottom, restricted cubic splines and fractional polynomials. And here's my fake data set. This is based on a real study. We were studying arthritis, and in particular, we were interested in the impact of arthritis pain, which is shown on the x-axis, the impact of pain on people's level of disability, which is shown on the y-axis. So disability in arthritis is a measure of inability to walk distances, the need for aids in walking, such as a wheelchair or a walker, inability to walk upstairs, and both pain and disability were measured using validated instruments. And the relation shown here, this, as I said, is fake data, but this is an approximation of what we do see in our data. And more to the point, this is a sort of relationship that we often see in healthcare data, where people with more pain report more disability, but only up to a certain level. And at around a pain level of 60 or 65, we see that the disability starts to level off with very little increase in disability beyond that point. So pain is our continuous predictor in this example, and disability is the outcome or the dependent variable. I'm going to tend to use the words predictor and outcome. You may be more used to hearing them called the independent and dependent variables. Now, the first way of dealing with modeling a continuous predictor taken from the table is dichotomization. And I think we're all guilty of this. If you look at Steyerberg's table, he says that dichotomizing is a bad idea. Those are his words, not mine, but I'd have to say I'd probably agree. Nevertheless, we do it a lot. Well, okay, I'll admit that I've done it. I'm sure that none of you have done it, but I'll admit that I've certainly dichotomized continuous variables. If there's no theoretical guide to where we should take the cut point, we tend to use the quantiles. So here I've taken my cut point as the median value of pain, which is 53 in this example. I've said that people with pain scores higher than 53 have high pain, and people with scores lower than that have low pain. And you can see the red lines are the predicted lines that I would get from a regression. And you can see that at least on the left-hand side, I haven't done a very good job of capturing what's going on in my data. I've said that everybody with low pain, anybody with a score below 53, is going to have an outcome of about 55, a disability score of 55, and that just clearly does not capture what's going on in the data. Because of the way I happen to have simulated the data, I'm actually doing quite a good job of capturing what happens for people with higher pain. They're all predicted to have the same level of disability, a disability score of around 76. You can also see from this example one of the hallmarks of dichotomizing, which is that there's a discontinuity in the predicted values, a sudden jump. If you've got a pain score of 53, you're predicted to have disability score of around 55, but your neighbor with a pain score 1 point higher suddenly jumps to a predicted disability of 76, 21 points higher. And this just isn't our understanding of the way things work in real life. Almost never would you see a sudden jump in anything. This is what happens when you use dichotomization. So there are a couple of reasons why we tend to dichotomize. First of all, it makes the analysis and the interpretation of the results really easy. In the graph that I just showed you on the previous slide, people with low disability people with low pain have a disability that's 21 points lower than people with high pain. That's a really easy, simple thing to say. Another reason that we often dichotomize is it does mimic the way that clinical decisions are often made. In the end, for a clinician, it comes down to making a decision between treating or not treating a patient, or prescribing a drug or not prescribing a drug. And so patients tend to get dichotomized. If you have blood sugar level over a certain point, you're said to have diabetes. And if you're below that, you don't have diabetes. And the same thing with hypertension. Now, I'm oversimplifying, obviously, because we do say, okay, I don't like the fact that your blood pressure is as high as it is, but we're not going to put you on a drug yet. But ultimately, people have to be put on a drug or not put on a drug, or they have to be offered surgery or not. But there are a lot of downsides to dichotomizing, and I've listed them, at least some of them here. There are two sorts of continuous variables that you would use in a regression. The first sort is when the continuous variable is the one that you're really interested in. So we might be interested in the impact of arthritis pain on disability after adjusting for other covariates. So the pain is the variable that we're really interested in. And when we dichotomize, that's equivalent to a huge loss of power. It's equivalent to losing about a third to a half of the number of observations that we have in our data. Well, maybe if you have an awful lot of observations, that isn't a problem. We were working with survey data, and losing the power of half of our data was quite an impact. As I showed, it does lead to an unrealistic model, and it makes it impossible to detect whether the impact of our variable is linear or nonlinear. In other words, we can't detect the actual pattern of the relationship. Now, the second kind of continuous variable would be one that you're just adjusting for. So it's a confounder. You want to adjust for it before you look at the impact of the treatment that you're interested in. So, for example, age might just be something we want to adjust for in our regression model before looking at the impact of arthritis pain. If you dichotomize a variable like that, what it does is increase the probability of false positives for the variables that you're interested in. So it increases the probability that you're just going to arrive at the wrong conclusion. Another problem with dichotomization, as I mentioned, is that the choice of cut point is problematic. The choice of cut point can impact what your final conclusion is, whether you decide that there is or is not a significant association between the predictor that you're interested in and your outcome. Sometimes we go hunting for a good cut point, and that's even more problematic. Do I get a significant result if I take my cut point here? Well, what about here? Well, maybe I'll try here. And in that case, you really need to adjust your p-values to account for the fact that you've gone looking for the best place to make your cut point. And as you can imagine, when more than one variable is dichotomized, the results are just likely to be misleading. Your conclusions are likely to be wrong. I've included here two really nice, easy to read references. The first by Royston, who is a statistician who just happens to write in English as opposed to math. And the second one is from our wonderful methodologist here at ICES, Jiming Fang. And this is a SAS Global Forum presentation that he gave a while ago. So both of these presentations will discuss in more detail what happens when you dichotomize a continuous predictor. So you can have more categories, and if you have more categories, you will, of course, come closer to approximating the shape of the relationship. Again, with no theory to guide where I should take my cut points, I've taken them at the quartiles of the relationship. And I've captured more of the idea of what's going on. You can see that between the first quartile and the second quartile, I can see that I have a big jump in disability. And I can see that for the last two quartiles, there's almost no change in disability. But I still have these big jumps in between at my cut points. So I'm still not doing a really good job of modeling the relationship between pain and disability. Of course, if I add more and more cut points, more and more categories, I'll come closer and closer to the proper model. The next choice on Steyerberg's table is a linear fit. And he says in his table that a linear fit is, quote, often reasonable as a start, unquote. And just to look ahead as we get to restricted cubic splines and fractional polynomials, we'll certainly be looking at tests to see if a linear fit is good enough. It's clearly not a good fit here because you can see that it fails to capture the two characteristics of this curve. It's not capturing that steep increase on the left-hand side, and it's certainly not capturing the leveling off on the right-hand side. It predicts that as pain increases, the disability will just keep increasing and increasing. So we're going to overestimate disability at both the low end and the high end of the curve, and we're going to underestimate it in the middle. So the next choice is a polynomial. And the most common one that we use is a quadratic, meaning that we add the square of the predictor. Unless we get really enthusiastic about this, we seldom go beyond a quadratic, although as we get to our last two methods, we certainly will. So quadratic is getting pretty racy here. And for the sample data set that I've been using, that would mean that we'd include both pain and the square of pain as predictors in the regression model. Now, quadratics, that is using the square, are limited to capturing two relationships, either a U-shaped relationship or an inverted U-shaped relationship like the one shown here. And the thing to notice about this quadratic relationship is that on the right-hand side, in this case, the predicted values increase, and then they decrease again on the right-hand side at exactly the same rate as they were increasing. And mathematically, this is just what quadratic relationships do. They go up and they come back down, or they go down and they come back up. But they are constrained to behave in this manner. So there is no way to capture an asymptote using a quadratic polynomial. Here's the quadratic fit for my pain and disability data. You can see that it actually does a pretty good job of capturing the relationship, so you can guess how I generated my fake data. But what you can see is that the fitted line starts to come down again at the top right-hand corner. It has to start to come down. If I'd had more data, it would come down still further. So this predicted model is predicting that in the extreme, as pain gets very high, the disability will start to lessen. And that, of course, is one of the problems with using polynomials. But here, as I said, we've got a pretty good fit. And next on the table are log transformations. Log transformations are actually pretty wonderful. They work extremely well in a lot of cases. You'll see, in fact, that they work extremely well on my data. That's just a happenstance of the way I generated the data. Now, the log transformation is only one of many transformations that you can use on your data. And I'm not going to go into all the choices because otherwise this would become a talk on transforming data. The log transformation is probably the one that we use most commonly in healthcare. The problem, the disadvantage of using the log comes when it comes to interpreting the parameter estimate, the beta 1. When you took high school math, you probably learned that the slope of a line tells you how much the outcome is going to change for each 1 unit change in the predictor or x variable. Well, when you take the log of your continuous variable, this interpretation changes. The beta tells you how much the outcome is going to change for each unit change in the log of your continuous variable, and that changes it from the amount of change for an absolute change in the continuous variable to the amount of change in the outcome for a relative change in the continuous variable. If I model pain on the log scale, then I'm saying that moving from a pain score of 10 to a pain score of 20, that is doubling the pain, is going to have the same impact on disability as moving from a pain score of 20 to a pain score of 40, because in both cases I'm doubling the pain. So here's my log fit to the data. I took the log of pain, and as I said, this does a very good job of fitting the data. I've shown the regression equation. I've got an intercept of -24, and I've got a slope of 23.52 times the log of pain. And this is interpreted as saying that each 10% increase in pain increases the disability score by 2.24 points. So whether I go from a pain score of 10 to a pain score of 11, which is a 10% increase, or I go from a pain score of 50 to a pain score of 55, again, a 10% increase, I'm predicting that the change in disability will be the same. You can work out the arithmetic on your own and make sure I didn't make any mistakes on this slide. I will give you on my next slide a website that you can go to if you ever need to understand how to interpret log transformations. And if you're really puzzled, I did work it out at the very end of this presentation. So if we have time and people are really pained by this slide, we can go through the math. But what I'm going to show you next is one of the secrets, or maybe not so much of a secret, to data analysis. This is a website belonging to the IDRE, that stands for Institute for Digital Research and Education at the University of California, Los Angeles, and we just call this the UCLA website. And if you are ever stuck for knowing how to do a particular analysis, whether you're using SAS, SPSS, Stata, or R, or you need to know how to interpret some results, one of the first things that you should do is Google UCLA and SAS or Stata or SPSS or R, plus whatever it is that you're stuck on, because this website has some truly wonderful explanations for all sorts of statistical analyses, including step-by-step, how do I interpret the SAS regression output. The particular website that I've sent you to here is, as you can see from the name, how to interpret a regression model when some variables are log transformed. And this particular portion of their website will walk you through interpreting the output when you've transformed one of the predictors, when you've transformed the outcome variable, or when you've transformed both the predictor and the outcome. So this is, if you take away nothing else from this talk, this is going to be worth the time that you spent. So I'm going to stop here and just ask if there are any questions before we plunge into restricted cubic splines.
Okay, I've unmuted you, Ridwan.
Oh. Okay, hello, thank you.
You're welcome.
Thank you for the nice presentation. Yeah. So when you talk about the adjusting for covariates, I know you didn't really talk much about it. That's why I said my question would be a bit unrelated, but I'm kind of doing some regression analysis. My background is a bit different from public health. I'm kind of from engineering background. So I want to know if in adjusting for effect of covariates in a regression model, for example, I want to adjust for effect of age and sex. Is it reasonable to also consider like interaction between like age and sex in the regression model, or just using the age and sex as covariates is just enough to adjust for the effects of age and sex in the regression model?
Okay, so the question is, if you're interested in adjusting for age and sex, should you also include an interaction term? Now, the answer to every statistical question is it depends. That is always the correct answer to every question. You shouldn't just go putting interactions in willy-nilly. Let's put in interactions between every single covariate that we've got. But if you have reason to think that it makes sense in the context of your study to look for an interaction between age and sex, you would certainly put them into your model. And in fact, we can draw scenarios where you might fail to find an effect if you fail to include an interaction term. So yes, if there's reason to think that there is an interaction, or that an interaction is a reasonable thing to test for, then you would include that interaction in your model. And I should add, of course, I forget that here at ICES we tend to have like 10,000 observations in our data set, so adding an interaction isn't a problem. But you are also limited by the number of observations in your data set as to whether or not you can start adding interactions. So that answer was very much, it depends. An age and sex interaction is in fact quite a common interaction to add into a regression model. So I hope that
because
answered your question, although it wasn't an absolute answer. You must do this or you must not do this.
Okay, because in most kind of similar research that I see in kind of adjusting for effects of any covariate, like they just use that covariate alone in the model. There's nothing like maybe interaction or so. So I'm kind of bothered, like, is it just kind of, you just have to use it directly, or it's not really, really necessary to consider interaction in those cases?
Well, as I said, you should consider whether or not you can include a particular interaction in a regression model. Depends very much on the area that your data came from and whether it makes sense to expect an interaction or the interaction makes sense. You typically would not add interactions just willy-nilly. Let's just add all possible interactions and see what falls out. You're very likely to find something that's came up by chance alone. So it's very much up to the expertise, the content knowledge, the subject content knowledge of the person creating the regression model or the person directing the research, what interactions you would add. Remember that you're going to have to interpret the interactions if you find significant interactions, or if you fail to find significant interactions. So you don't just add them because it's possible to add them. You add them because there's a reason to add them.
Oh, thank you very much.
But I would never discourage anybody from adding interactions, although I have to say that some of the researchers I work with get rather unhappy when I
get those
with some of the interactions. So I'm going to move from sort of some simple things to look at to the two topics, as I said, that are the bulk of this presentation. And the first one is restricted cubic splines. And I'm going to start, I guess I should start by looking at my notes, which say that I'm supposed to say, if you knew the form of the relationship between your continuous variable and your outcome, then of course we wouldn't be here. You would use the correct form to do your regression. Usually we don't know the form of the relationship, and so what we're trying to do is discover what the form of that relationship is. And that one of the ways to discover what the relationship is between a continuous predictor and an outcome is to use a restricted cubic spline analysis. I'm going to start with a picture of a real spline. So here we have some flexible tubing, and along its length are some weights, and these weights are called ducks because somebody thought they looked like ducks. I think they look like whales personally, but they are called ducks. And the aim of this photograph is to show you what the cubic splines are going to be doing. So the ducks, or the weights, can be moved anywhere along the points in your data. They can be placed at points in your data where you want the line to pass through. But you can see that in between the weights, this flexible tubing is able to take on any curve that it wants to take on. In fact, you can see that it's curving in one direction between the first two ducks, and it's curving in another direction between the second two. And the other thing that you can see is that where this flexible tubing passes through one of these ducts, it passes through smoothly. You don't see a sharp kink in the flexible tubing. We're going to be doing the same sort of thing with our data that this flexible tubing is doing here in this photograph. Splines like this one were originally built out of flexible strips of wood. They've been used for centuries. They were used in boat building originally. And the ones like this were used to design cars, and this may scare you a bit, but they were used to design aircraft. If you take a look at the website that's at the bottom of this slide, there's a really great picture of an engineer at Boeing Aircraft using one of these splines to design an aircraft. Now, it's not done that way anymore. It's done with computers. And in fact, the fellow whose website I took this picture from, Carl de Boer, was one of the mathematicians who did the work that developed the algorithm that allowed splines to be modeled using computers. So this spline looks, nice and simple. It's a nice piece of flexible tubing doing what flexible tubing does. But how do you get this into a computer algorithm? Well, he was one of the first people to work on this. So that was your history lesson for today. And that was by way of saying that we are going to do something similar for our regression. We're going to allow curvature to capture the pattern of the relationship between our continuous variable and the outcome. We're going to divide our x variable, that is our continuous predictor, into segments, and we're going to allow different curves for each segment. So we're going to allow some of the curves to be concave, and some of them to be convex. Between the segments, we're going to allow the curves to do whatever the data wants them to do. But we're going to force those curves to join at our ducts, and we're going to force them to join smoothly, just like in this picture. So I was looking for a data set that would be good for illustrating what restricted cubic splines could do, and I came up with this function, which does not represent anything at all except a challenge to restricted cubic splines, because if we can fit this particular pattern, we can probably fit anything. So the blue points are my data points, and the green line is the actual function that I'm going to try to fit. So I've got a continuous predictor x, and I've got an outcome variable, which is y. So analogous to the photograph that I showed you of the flexible tubing, I'm going to take the range of x values, and I'm going to split that range at certain values, which are now called knots. Unfortunately, we're not calling them ducks anymore, even though that was kind of cute. But we're going to split the x values, or the predictor values, at certain points, which we're going to call knots. And we're going to fit a separate regression curve in between each pair of knots. So we have three decisions to make: how many knots, where are we going to place them, and what degree of polynomial are we going to use for the curves that fit the data in between the knots. And I'll also explain what I mean when I say that we require the various curves to fit smoothly. So I'm going to answer the third question first. What degree of polynomial are we going to use? Now, the methodology is called restricted cubic splines, so you get exactly one guess. We're going to be using cubic polynomials. So we're going to have an x and an x squared and an x to the power 3 term in our model. Why cubic? And that's because the cubic is the smallest degree polynomial that allows for inflection. So you can see a cubic curve over there in the bottom right-hand corner. You can see that it can change direction. It can change from concave to convex. We don't want to use, powers to the 10, because every time we add a variable to our regression, every time we add a power to our regression, we're adding additional degrees of freedom. And we don't want to just add useless degrees of freedom to our model, especially if we only have a small data set. We also don't want to overfit the data. We can add increasing polynomial terms and get an excellent fit to our particular data set, but the model that we get won't necessarily fit anybody else's data set looking at the same problem. So we don't want to overfit. So cubic polynomials, where are we going to put the knots and how many are we going to have? Now, one of the things you're going to find out about restricted cubic splines, and we're going to see it again with fractional polynomials, is that both these methods are very much driven by the question of what works, not driven by theory, but by what have we seen works in practice to give us a good fit to our data. So here we have two answers as to the number of knots. I've got the references later on, but Stone said 5 knots are sufficient. And Frank Harrell came along a couple of years later and he gave a bit more variation. He said if you have less than 30 observations, you should only use 3 knots. If you have more than 100 observations, you should use 5, and you should use 4 otherwise. Where are we going to put the knots? This comes from Frank Harrell's book, and the reference is, again, as I said, it's a couple of slides further on. Unless you have a theoretical reason for placing the knots at a certain point, they're going to be placed at certain quantiles of your range of x values. So the location of the knots does not depend on the actual values of x. It depends on the quantiles of x. In other words, we're going to put more knots where there's more data and fewer knots where there's less data. So if you have 5 knots, if you've decided that 5 is good enough following Stone and Harrell, you will put the first knot at the 5th percentile, the second one at the 27.5 percentile. The third one goes at the median. I'm looking at this row here. The fourth one at the 72.5th percentile, and the last one at the 95th percentile. So you can see that below that there are going to be about 5% of the data points are going to be below the first knot, and another 5% are going to be above the last knot. And again, these are percentiles of the data. These are not values of x. These are percentiles of x. What this means is that if most of your data is concentrated at one end of the distribution of x or the other end, if most of your values are small, you're going to have all your knots down at the small end of the data. If most of your values are large, your knots are going to be up at the large end of the data. And this is important because what you want to do is you want to do a good fit where you have most of your data points. You don't want to have a regression that's doing a really great job of fitting a few outliers at the expense of not fitting most of the data points. Now, the methodology is called restricted cubic splines rather than just cubic splines. And the word restricted means that we're going to have a linear fit below the first knot and a linear fit above the last knot. This has been found to fit the data better, and it also reduces the number of degrees of freedom that we have to use in order to fit the restricted cubic splines. So if we have k knots, and k is usually 5, then we're going to have, I think I got this right. We're going to use k minus 1 variables. So k minus 1 degrees of freedom are going to be added to our regression. One of those degrees of freedom is our original predictor, x, and then there are an additional k minus 2 cubic variables. So if we have 5 knots, we're going to have 4 variables in all, our original variable x, and 3 new variables. And I'm going to show you how to calculate those new variables in just a minute. So this is compared to just 1 degree of freedom if you had a linear fit. So we have added degrees of freedom to our model. And again, not a problem if you've got lots and lots of data, but definitely a problem if you've got small amounts of data. So the new variables that are going to be added to our regression, they are really, really ugly. They're shown down here at the bottom of the slide. And I'll tell you right now, you are not going to have to calculate these by yourself. If our knots are at T1, T2, up to T5, if you've got 5 knots, you will have to calculate 3 new variables using this equation here. What is this equation doing? Well, you can see that it's got a cubic term. It's got lots of cubic terms. So you can see that we're going to be fitting some sort of cubic polynomial. These complicated looking fractions here are what ensure that where the curves meet, they meet smoothly. So this ensures that your curves are going to meet in between when the knots, that is the curve that's fit between knot number 1 and knot number 2, is going to meet the curve that fits between knot number 2 and number 3, which is going to meet the curve which fits between knot number 3 and knot number 4, and so on. And this plus notation here says that we're going to have a piecewise fit. This is what ensures that we get one curve for the first part of the range of x values and a second curve for the second part of the range of x values, etc. So these plus signs down here in the equation are what tells us that we're going to be fitting separate curves to the different parts, the different ranges of our x value. Now, as I said, you don't have to program this equation because there's a macro. Now, all of the software that you might be using, whether it's SAS, Stata, or R or SPSS will calculate splines for you, so you're not going to have to program that particular equation. My personal preference is to use a macro, and the reason for that is that I have to admit that I am never really quite sure what SAS is doing. And so I like to be able to see what's happening, and I like to use a macro where I can go and look at the code and see what my new variables, how they're actually being calculated. I like to have them in my hot little hands. However, you may be on much more friendly terms with SAS than I am, and you may just want to use SAS's splines. I actually got in a lot of trouble for saying that I didn't like to use SAS's splines when I presented at SAS Global Forum. They were not too pleased with my saying that, but anyway, I think they managed to survive. This website goes to Vanderbilt University, and this will lead you to a whole bunch of macros provided by Frank Harrell. And one of those macros will be the RC spline macro, and he's got a whole bunch of other macros that do useful things. So you can go to this website and download his macro, his RC spline macro, and all you have to do then is include it in your SAS program. Now, I've included some SAS code here showing how to use restricted cubic splines in a regression in the hopes that it will, again, give you more of an idea of how the restricted cubic splines are working in practice. I've decided that I'm going to use 5 knots for my data set. I looked at the table from Frank Harrell's book, and I found out what percentiles I was going to have to use: the 5th, the 27.5, 50, 72.5, and 95. And because I'm using SAS, I've used proc univariate. I've given it my variable x, and I've asked it to find out what the percentiles are of x. So what's the 5th percentile? What's the 95th percentile? And I've asked it to put those percentiles into an output data set. This peculiar piece of code right here is reading that output data set from proc univariate into my example data set. So I will now have the percentiles available to me in my data set. They're going to be called P5, P27_5, P50, and so on. And now all I have to do is call Frank Harrell's macro, RC spline. I give it the name of my continuous variable, which is x, and I give it the name of the variables that are holding the percentiles. And it will produce 3 additional variables called x1, x2, and x3. If age had been my continuous variable and I'd put age in here instead of x, it would have produced age 1, age 2, and age 3. So it's very, very simple. Once you've downloaded the macro, it's very simple to create the spline variables for your data set. And once I have them, all I have to do is fit the regression in the usual way that I would fit a regression using SAS. So here I've just used the GLM procedure. Here's my model. I've got y as my outcome variable. I have x as a predictor, and here are my 3 spline variables, x1, x2, and x3. So it's as simple as creating the 3 new variables, which, as I said, fortunately, you don't have to program for yourself, and just adding them into the regression. And if we had other covariates that we wanted to include in the regression, and I'll show you some examples, we would just add them into the regression as well. And here's the fit I got to my data set. Now, it's not a perfect fit. We haven't captured that peak, and we haven't captured that dip off at the right-hand side. But this is certainly much better than I could have done on my own. Certainly a linear fit wouldn't have worked. Certainly using a quadratic wouldn't have worked. So this has worked pretty well considering the data set that I gave it to work with. And if I'd actually used 7 knots, I would have really done quite a remarkable job of fitting that particular function. Actually, I think that's pretty impressive because that was a very strange function that I used. Now, When I used restricted cubic splines, all I did was take my original continuous predictor and add some additional variables. In this case, 3 new variables, each of which is a transformation of the original predictor. I haven't touched my outcome variable at all. And that means that I can use this methodology with any kind of regression. If my outcome variable had been binary, I would use logistic regression. If my outcome variable had been time to death or time to event, I would use survival analysis. So restricted cubic splines can be used to determine the relationship, the shape of the relationship between a continuous predictor and any sort of outcome, just by using the type of regression that you would use that is appropriate for the type of outcome variable that you have. Now, I said that one of the things that we want to know is, in fact, first of all, we want to know whether our continuous predictor is needed in the model at all. And second of all, if it is needed in the model, is a linear fit good enough? Do I need that really ugly equation that I just showed you? These tests for the significance of the predictor and the test for nonlinearity are done by comparing the model deviance of the model that includes all the spline variables, including the original variable, to the model that doesn't have any of the spline variables. When you compare, so I'll call that the null model, when you compare the model deviance of the model that has all of your spline variables with the deviance of the model that doesn't have any, that change in deviance tests for whether you need to include that continuous predictor in your model at all. If that test is significant, yes, we need to include X in our model. If that test is non-significant, we can drop the whole thing. If we decide that we do need to keep our continuous variable, the next test will compare the model deviance of the model that just has the linear form of the variable to the model deviance including all of the spline variables. If that test is significant, yes, we've got a curve. We need to include the spline variables. If that test is not significant, a linear fit is good enough. And I'm going to show you what I mean by all those words on the next slide. Now, this is more SAS code, but you can do the same sorts of, and I assume you can do the same sorts of things using SPS or Stata. Stata almost certainly, and probably are. One of the wonderful things about SAS syntax is that it's sometimes not the same for every procedure. So I've given you 2 different examples here, 2 different regression models. And I'm going to, in both cases, I'm going to test, first of all, to see if my variable belongs in the model at all. And second of all, if it does belong in the model, is a linear fit good enough? And thanks to Jiming Fang for this notation. So my first example, I've got time to death, and not everybody died. Some of my people were censored, so I'm going to use survival analysis. In SAS, I'm using the PHREG procedure on some survival data that I have. I've got 3 predictors: age, sex, and whether or not the person has diabetes. Age is a continuous variable, and I'm wondering about what the relationship is between age and time to death. Is there any relationship at all? Probably there is. Age is a very good predictor of time to death. If there is a significant relationship, is it curved or is a straight line good enough? So here are the 2 tests that I referred to on the last slide. First of all, I'm going to test to see if I need to include age at all. I'm going to test to see if I need to include age, age 1, age 2, and age 3. These are my 3 spline variables, and this is my original predictor. Do I need to include them, or can I drop all 4 of them from my model? If this test is significant, I will include all of these variables for now. If this test is not significant, I get to drop age completely from my model. Assuming that this test is significant, and it probably will be because, as I said, age is a very good predictor of time to death, the next thing I want to know is whether a linear model is good enough. And that means I'm going to test to see if I need to include age 1, age 2, and age 3, or whether it's good enough just to stick with age, the linear predictor. So if this test is significant, I'm going to have to incorporate my curve. If this test is not significant, I just need to use age. In my second example, my outcome is COPD, whether or not the person was diagnosed with COPD. That's a binary outcome, so I'm going to use logistic regression. I've decided to use the GenMod procedure to implement my logistic regression. The descending option, for those of you who aren't familiar with SAS, the descending option here just ensures that I'm predicting that the person will have COPD, because the default in SAS is to predict that the person will not have COPD. I have the same predictors because I'm not very imaginative, so I have age here, sex, and diabetes, and I've included the 3 spline variables, age 1, age 2, and age 3. I've said that I want to do logistic regression. Now, the syntax for the tests looks very similar to the syntax used for my survival analysis, and it's doing the same thing. I want to know, first of all, whether I need age at all. So I've asked it to tell me about age 1, age 2, and age 3. Do I need those variables? If this contrast is not significant, I'm finished. I drop age completely. I'm done. If this test is significant, if the p-value is small, that tells me I need to keep age, and the second test will ask whether a linear fit is good enough or whether I've got a curve. So again, the 2 tests, one to see if I need age at all, and the next test to see if I need to include the curves or whether a linear effect is good enough. And just to belabor the point, here's another example. Now my outcome variable is distance to the hospital. It's a continuous variable, and so I'm going to use ordinary least squares regression. I'm using GenMod again, the GenMod procedure, which will also do ordinary least squares. And again, I've got the contrast asking, first of all, whether I need to include age at all, and second of all, if I do include it, is a linear fit good enough? I know that some of the people listening are at ICES, either here at ICES Central or at one of the satellite sites, and you have access to the linear test macro, which was written by Jiming Fang. So all of this work is done for you. You just use the macro, tell it what kind of model you want. Is it survival? Is it logistic? Is it ordinary least squares? Is it Poisson? And it will do all of these tests for you. The rest of you will have to do a bit more work, but it's really not bad. Trust me. If you do decide that what you've got is a curved fit, you want to get a graph of that relationship. At ICS, we tend to have very large data sets, and that in turn means that a variable or a set of variables can be statistically significant without really being very useful. So if you reject the linear test, meaning that the amount of curvature in your relationship is statistically significantly different from 0, that doesn't necessarily mean that it departs from linearity in any way that's important. So my suggestion to you is that you still go on to graph the relationship and that you share the graph with the project team and decide whether a linear fit is good enough or whether there is enough curvature that you want to retain the curve. So it's a question of good enough versus complexity. I've got one example of a research project that used splines. They are being used more and more, certainly at ICES, and I think more and more in practice by other researchers as well. But I found this one example was a very nice example of using splines. We've also used them to look at the relationship between surgeon experience, number of previous surgical procedures that a surgeon has performed, and the probability of having adverse outcomes from the surgery, a nonlinear relationship between surgical the surgeon's experience and the probability of outcomes, and has been used in a number of other applications, but I thought this was a really nice study. So this really great study was done by Maria Chu here at ICES. The x-axis is body mass index, BMI, and the y-axis is a measure of the incidence of diabetes. BMI is used to predict the risk of diabetes, in particular, based on information coming from a largely Caucasian population, which was certainly Toronto back in the early 1980s. A BMI of 30, which puts people just over into the obese range, was viewed as sort of a cut point for starting to worry about whether the person would have diabetes. So somebody with a BMI of 30 or higher would be a good candidate to test to see if they had diabetes. You can see that on average for a Caucasian population, if you use this cut point of 30, the probability of having diabetes or the incidence of diabetes is 11 people per 1,000 person years. What does that mean for people who are non-Caucasian? The same risk, 11, is obtained on average at a BMI of 25 or 26 for people who are Black ethnic relation, Black ethnicity, and 25 for people of Chinese ethnicity, and 24 for people of South Asian ethnicity. These ethnicities come from the Canadian Community Health Survey. Now, 24 puts you in the range of a healthy BMI. I think 26 puts you just over into the overweight range, but certainly not into the obese range. So what you can see is that for people who are non-Caucasian, that same risk of 11 is achieved at a much lower BMI, suggesting that the current guidelines for testing, which refer to a BMI of 30, are probably inappropriate for people who are non-Caucasian. So a very nice study, and you can see that these relationships between BMI and risk of diabetes are definitely nonlinear and would be hard to capture other than using something like a restricted cubic spline fit. So Maria used restricted cubic splines to get these curves. I've given the reference at the bottom if you want to get a much better description of the study than the one that I gave. Now, there are a couple of drawbacks to using restricted cubic splines. First of all, for small data sets, we have added new predictors, so we've used up some degrees of freedom. I'm sure that when you looked at those equations for the new spline variables, you started to wonder how on earth you would ever explain those to anybody. So there is a difficulty in presenting and interpreting the results. And really, I think the only way to present or explain the results is to use a graphical presentation. Now, I mentioned earlier that there are two kinds of continuous variables that you'd put into a regression model. One type is the kind that's where the continuous variable is the variable that you're very much interested in. In Maria's case, it was BMI. And in that case, you really are going to have to resort to a graphical presentation of the relationship between your continuous variable and your outcome if you've used restricted cubic splines. The other kind of variable is just a confounder. It's something that you've adjusted for, and you may not care to actually present the relationship. In that case, you may get away with simply saying, we adjusted for age using restricted cubic splines in our model before looking at the effect of treatment, which is what we were interested in. So graphical presentation for the variable of interest, and simply a note that you adjusted for variables which you wanted to adjust for, but you don't care to discuss what the relationship actually was. So this is my take-home message for using restricted cubic splines, is that you will be presenting the results using a graph. Here are the two references. First of all, to Harrell. This is a great book, Regression Modeling Strategies. Frank Harrell is a really wonderful applied statistician. So not so much what does the theory insist that you can do. If you stick to the theory, you'll never get anywhere in applied statistics because nothing ever fully meets all of the assumptions that are required. And secondly, I've given you the reference to the stone. It was just a comment saying 5 knots are good enough. So I'm going to stop here for 2 reasons. One is to see if there are any questions, and also a sort of 5-minute break.
Great, thanks very much, Ruth. We do have a couple of questions in queue here. So would you like to take them now?
Yeah, that would be great.
Okay. How do you deal with regression when data are missing for continuous predictor variables?
Oh, that's like a totally different topic. Imputation of missing variables is a totally different topic, and we could spend another 2 hours on that. So you would certainly, as I'm sure the questioner and everybody else is aware, if you stick observations with missing values into your regression, they will get dropped. Therefore, we would normally try to impute those missing values. There are many, many ways of imputing missing values. What we used to do in the bad old days before we had some good computer programs was just stick the average value in. That's not the right way to do it. These days, if you're a SAS user, you'd use SAS's imputation procedure. And what that will do is it will use other information in the data sets to try and figure out what the an appropriate value of the missing data point is. And it will, in fact, produce 5 new data sets in order to capture the variability that's been introduced by imputing some of the values. So that was a really short answer to a, as I said, a really, really big topic.
Okay.
But yeah, you would probably impute the missing values in some way.
All right. Shall we go on to the next one then?
Sure.
Why this type of spline? There are more powerful types.
Well, the reasons for using the cubic spline is, if that's the answer, is, as I said, we are not at ICES typically concerned with degrees of freedom, but in many, many applications where you have a small data set, in fact, I'm working with one right now where we've got only 100 cases, you do start to worry about losing degrees of freedom. So you don't want to go to higher order polynomials and use up degrees of freedom if this method is good enough. And I hope that I showed that, in fact, it does a very good job of modeling even very complicated relationships. But certainly if you have the data and the software, there's no reason why you couldn't go on to use other spline methods. I'm actually more interested in getting people to consider splines and to explain what the spline is, how it divides, how the range of x values is divided into segments, and how a separate curve is fit in between each segment, than in saying, well, you have to use restricted cubic splines.
Okay, thank you. We'll go on to the next one.
Sure.
Could you say a little more about modeling interaction between nonlinear variables, say BMI, and another variable, say race, in your diabetes example?
Okay. You do it in the usual way, first of all. That is, that's quite a complicated question because race, of course, is categorical. Maria had 4 different groups, so she's got a 4-category variable. And by introducing splines, we've got now 4 variables that we're using to model our continuous variable of BMI. So your interaction term is going to have a lot of degrees of freedom because you've got 4 spline variables and you've got 4 race categories. So you're going to include all of those interactions in your model. In other words, you're going to have your 4-category race interacting with BMI, and you're going to have your 4-category race interacting with BMI 1, that is your first spline variable, and your 4-category race interacting with BMI 2, and again, your 4 categories of race interacting with BMI 3. So you're going to have added a lot of extra terms to your model. Now, if you're interested in, if your Caucasians were your reference group, then a lot of those regression terms are going to drop right back out again because your other 3 races were not, if it's your reference term, the other interaction terms don't apply. And similarly, when you want to get the graph of BMI versus, let's say, South Asian, many of those terms that you just added to your model are again going to drop out because they don't apply to South Asians. So the interaction between Chinese and BMI, BMI 1, BMI 2, BMI 3 are going to drop back out again when you go to calculate the predicted values. So you're going to add a lot of additional terms to your model. And then you've got 2 choices. One is to look at all those regression coefficients and do the calculations by hand. And the other way is to ask SAS to give you the predicted values for the various values of BMI and the various values of race. And SAS will do that. I don't want to belabor SAS, although it's the only language I know. But basically, you can give SAS a fake data set, which has all the different values of BMI and all the different values of race. So all of the combinations of race and BMI, no other variables because you don't actually have an outcome for any of these people. Give SAS a fake data set with all of these possible combinations in it, and SAS will give you the predicted values. So that is one thing that you can do. And as I said, the other thing that you can do is simply do it by hand once you've got all the regression coefficients. So, of course, you can't see me. I'm sitting here waving my hands in the air, so telling you how to do this. But basically, you just add all the interaction terms to your regression model, and then you try and figure out what they all mean. And if somebody's like totally puzzled by what I just said, I think email me, and I can put it down in email, and it might be easier to follow.
Okay, thanks very much. We'll go on to the next one. What is the test for the appropriateness of the number of knots? Just to look at the R2 and perform those tests?
There isn't really, as I said, both of these methods, this method and fractional polynomials, are both quite heuristic. So it's really basically 5 knots is probably good enough is the answer. You can certainly add additional knots if you have enough data to support it. And you can look at whether the R squared has increased. It will always increase because you've added more variables. R squared always goes up if you add more variables, no matter whether they're useful or not. The question is whether it's increased by a statistically significant amount or a useful amount. I don't have it at my fingertips. There is an article which tells you how to test to see if the increase in R squared is significant. I don't happen to have that at my fingertips, so I'm sorry I can't give it to you, but you can probably find it. It's quite an old article. So yeah, you can certainly add more knots and decide whether your increase in R squared is useful, given that you've added complexity and you've added degrees of freedom. So very much a heuristic, very much a, did I get anything out of this? You can also draw the graphs and see if they seem to have changed by very much. So that was a very applied statistics answer.
Okay, thank you. Next one. Is this spline type more suitable for simple curves?
No, as you saw, it did manage to do a very good job on my very unsimple data example. So yes, certainly most of our relationships, you know, that example that I came up with, that example with that ridiculous curve that went up and went down and had peaks, and really in healthcare we do not get those sorts of relationships. Most of the relationships really are fairly simple, and you really are usually going to get a fairly simple curve out of your regression analysis, because that's what the data show. It would be very unusual to have a relationship in certainly in healthcare, which suddenly went up to this high peak and then dove down again into a deep pit. That you really wouldn't expect to see that sort of relationship in your data, and so you really wouldn't expect to see that sort of fit in your data. You will usually get a reasonably smooth curve, a reasonably simple curve. That's not the fault of the restricted cubic splines. That's what the data show.
Okay, thank you. Maybe you've already addressed this question, but I'll ask it again. Why can't we choose where to put the knots?
If you have theory, and I should mention this, I've only ever once come across an example where theory told you where to put the knots. This was somebody who was looking at something to do with the cones in our eyes and visual acuity. Now we have cones in our eyes. We've got 3 kinds of nerve cells called cones in our eyes. Sorry for those of you who are totally bored because you know all this. And they respond optimally to 3 different wavelengths of light. So there's an example where the theory says we should put our knots at the 3 points where the cones respond optimally, the 3 wavelengths where the cones respond optimally. That is the only example I can think of where we've actually known where we would put the knots. If you don't know where to put the knots because there's no underlying theory, what you shouldn't do is go searching for where to put the knots. You shouldn't say, I'm going to put them here, 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 and here. I'm going to try here, 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 and here. No, maybe I'll try these other 5 points. If you go searching for the placement of the knots that best fits your data set, you need to adjust your p-values to say that you went searching for the best fit for your data. Because when you start to get down to that level of granularity where you're looking for the best place to fit your data, you're doing 2 things. One is you're trying to get a p-value where perhaps you shouldn't, so you're searching for the one that gives you the significant p-value. And second of all, you're overfitting your data at the expense of coming up with a relationship which might not be found when that relationship is searched for elsewhere. So if you go searching for the very best fit for your data, when you publish your methods, you have to say, I looked for the best placement for my data, and look, I found a significant relationship. And that's quite a different research question from saying, I've placed my knots where Frank Harrell told me to place my knots, and I found a significant relationship. I didn't go looking for where I was going to place my knots. So you're welcome to look for the best place to place your knots, but you have to admit to how many different things you tried before you decided on where you were going to settle. And you have to adjust your p-values accordingly.
Okay, thank you. Good advice, for sure. Next one. Thanks for presenting this topic. It's very informative. I have a question. For the interpretation of the results, if you are interested in understanding the treatment effects on time to death after controlling the age, which you have used the cubic terms in the model, how do you interpret the results?
Well, in the case where I have age and it's something I want to adjust for, and then I have a treatment effect, what I'm interested in is my treatment effect. Now, that's probably a binary. If it's a binary treatment, I treated them or I didn't treat them, then I interpret it the way I usually interpret it. The treatment effect, yes, no, is just a binary variable, and I would interpret it as such. I would not probably, if age was just something I wanted to adjust for, I would not try to interpret the impact of age, the shape of the impact of age. I would simply say I adjusted for age, and I got the best fit possible for the age effect by using restricted cubic splines. So I wouldn't try to interpret the effect of age, because that's not the purpose. That wasn't the purpose of my research. So what I'm going to do is go on to fractional polynomials, because I see that I've managed to. I was thinking might finish early, and now I'm seeing that maybe it won't. So I'm going to go on to fractional polynomials, and then we can save the rest of the questions. Or, of course, you might have some questions when I finish with fractional polynomials. So fractional polynomials are just another flexible method for modeling curved relationships using as few parameters as possible. So you can see that not everybody has the luxury of having thousands or tens of thousands of observations, and people are concerned with degrees of freedom. This method was proposed by Royston and Altman in 1994. I've got the paper at the bottom. We saw Royston earlier in one of our slides. Again, he's somebody who writes, as I like to say, he writes in English. What these two authors noted, again, is that polynomials lack flexibility, and we talked about that when I talked about our quadratics back at the beginning, and that they often fit badly at the extremes, so they can't be used to model data that has asymptotes. Other than that, this is very similar to conventional polynomials, except that, as you'll see in a minute, we're going to allow non-integer and negative powers. So we're going to expand beyond just squares and cubic terms. Fractional polynomials work by choosing m powers from a small predefined set of possible powers. Now, in the early papers, Royston and Altman wrote, we have found so far that models with degrees higher than 2 are rarely required in practice. So in practice, we're going to choose just 2 powers. And again, notice that phrase, in practice, is very much a heuristic. What we have found to work in practice. So there's not a theory underlying this that says that it has to be 2. This is what we found works in practice. And these 2 people work in healthcare research. Later on in their publications, in fact, they used m equal to 2 without even mentioning that there were other possibilities. So in practice, what you'll find is that people used 2 powers without exploring higher orders of fractional polynomials. When m is equal to 2, the set of powers that we're going to choose from are given here: -2, -1, -0.5, 0, where 0 is interpreted as being the natural log of your continuous variable, 0.5, which is the square root, of course, 1, which is just your linear term, and then a square and a cubic. Now, you'll notice from this that x, your continuous variable, is going to have to be positive, because we can't take the square root of a negative number, not without getting involved with imaginary numbers, which we're not going to, and we can't take the log of 0. So what you are going to have to do is if you have zeros or negative numbers in your data set, you're going to have to add a constant to x in order to make sure that x is positive. In healthcare, we rarely have negative numbers. Now, as soon as I say that, somebody's going to say, well, I have the perfect example of a continuous variable that is negative. But we really typically, our predictors tend to be 0 or positive. So number of emergency department visits, if that was one of your predictors, can certainly be 0, or the number of times that somebody has seen a doctor in the past 3 years can certainly be 0, but typically we don't have negative numbers. What we would usually do if 0 was one of the possible data values, and we had a variable like number of visits to a physician, or number of emergency department visits, or number of inpatient admissions, is we would typically add 1 to get rid of the zeros. The other context in which zeros arise could be lab test values. For example, serum creatinine or blood sugar levels, where a zero typically doesn't mean a zero, but what it typically means is that the level of whatever it is we're measuring was too low to be detected. And in that case, we wouldn't add 1 to the value because that could be really bad. That could have a real meaning to the data. We'd probably add the lowest detectable amount, so that instead of 0, we would replace that with the lowest amount that was detectable using the assay. And for that, you'd have to go and talk to somebody who was a subject area expert. So, okay, X has to be positive, and we're going to have to do something to get it to be positive if we have zeros or negative values in our data set. But other than that, here's what we're going to do. The degree of a fractional polynomial is just the number of powers that you've added to your model. So, for example, here I've got an FP1, a fractional polynomial 1 example. M is equal to 1, and the power that I've added is x to the power -1. So my model has an intercept, and then I just have x raised to the power -1, or the inverse of x. Here's an example of a model where m equals 2. I have x to the power -1, and I have x squared. These models look really strange because you've been told, and it's been beaten into you, and it's certainly been beaten into me, that if I have x squared in my regression model, I have to also have x in my regression model. That's the hierarchical rule, and it says that you don't have higher order terms in a model unless you have all of the lower order terms as well. And we've clearly broken that rule. So with fractional polynomials, you do not need a hierarchical model. So you can have these very peculiar looking models where you've got x, let's say x squared and x to the power -1. Now, each additional term that you add to the model is going to add 2 degrees of freedom. And you'll see how this plays out in a couple of slides. 1, because you had to search for the power, your choice of power. And 1, because once you had a power, you had to fit it, a regression coefficient to it. So here I've just repeated the set of powers that we're going to be considering, because the next obvious question is, we've only got 8 powers, and how is this enough to find the best model? I mean, this is a very limited set of powers to choose from. What Royston and Altman argued is that because the likelihood surface is usually quite flat near the maximum likelihood, and remember that when you're solving a regression equation, what you're looking for is the maximum likelihood, you don't have any need to precisely estimate the power. That is, you don't need to know whether it's a power of 3 or a power of 2.5 or a power of 2.1 or a power of 2. Because you're looking over a flat surface, it's good enough to approximate the best power. So 2 is good enough or 3 is good enough. The other argument that they make is that the powers which aren't included in this small set can be approximated by using the log plus one of the powers that is in the set. So their argument for leaving out all the other powers that could have been included is, first of all, that it's good enough to just use these powers, and second of all, we can come close enough to all the things that are missing by including both the log of x and the powers that are given. Now, how are we going to decide on the best model? How are we going to decide which powers from that set of powers, those 8 powers, we're going to include? Remembering that we're only going to include either 1 or 2 powers in our final model. This is kind of horrifying, this slide. It's maybe not quite as horrifying as the slide I put up showing how to calculate the splines, but it's bad enough. We're going to fit 44 models. Because we have 8 choices for m equals 1. We have 8 possible powers in our data set, in our set of powers, if we just choose one of them. We have another 28 choices if we are going to choose 2 powers from that set of 8 powers, and we're not going to allow the 2 powers that we choose to be the same. So we might choose a square and a cube. We might choose -1 and a cube, but we're not going to choose the same power twice. And then we have 8 more choices where we do allow the same power to be selected twice. Now, it sounds pretty stupid to select the same power twice because, after all, if you've put a cube in the model, you're not going to put another cube in the model. So we have some special definitions for what it means if you pick 2 powers and you pick the same one twice. I'm going to actually flip to the next slide because I've got an example which might be better than showing you the definitions. So if we've picked 2 powers, P1 and P2, and neither of them is equal to 0, our model is going to contain x to the power and x to that power multiplied by the log of x. So for example, if P1 is 2 and the second power is also 2, my predictors are going to be x squared and also x squared times the log of x. If I've picked P1 equal P2 equals 0, then the model is going to contain the log of x, because that's what 0 means, and also the square of the log of x. So my predictors will be the log of x and the log of x squared. Now, 44 regression models sounds absolutely atrocious, but in fact, all you have to do is calculate 8 new variables corresponding to x raised to each of those 8 powers, and then stick them into your 44 models in the various combinations. That still sounds pretty awful, but it's not as bad as it might sound. Now, we're going to determine the best FP1 model, that is the best model with 1 power, and we're going to find the best FP2 model, the best model with 2 powers in it. Best is defined by the one with the lowest deviance. So once you fit all possible FP2 models, you're just going to select the one that has the lowest deviance. And once you have all 8 FP1 models, you're going to select the best one, which is the one with the lowest deviance again. And then you're just going to compare the best FP2 model to the best FP1 model using the differences between the deviances, comparing those to a chi-squared distribution. That is a chi. It's not a very good chi, but that is a chi-squared. So let's talk a bit more about what this means, and then I do have an example. The first question that we want to ask is whether our x variable, our continuous variable, belongs in the regression model at all. So we're going to take the best FP2 model, that is the best model that has 2 powers in it, and we're going to compare it with the null model in which we've left x and all its powers out of the model completely. We might have other covariates, and in that case, the null model will contain those other covariates, but we're going to remove x entirely from our null model. We're going to compare those 2 models. We're going to compare the change in deviance using a test with 4 degrees of freedom. So we've got a chi-squared with 4 degrees of freedom. The change in deviance is a chi-squared value, and it's got 4 degrees of freedom. Why 4 degrees of freedom? Remember that each of the powers that I stick into my model has 2 degrees of freedom, one because I had to decide which power to use, and a second degree of freedom because I then had to estimate the parameter estimate, the beta. So since my FP2 model had 2 powers in it, it has 4 degrees of freedom. if this test is not significant, comparing my best FP2 model against the null model, I can quit. X does not belong in my model at all. The next question I'm going to ask is question number 2. Do I need an FP2 model, or is a linear model good enough? So I'm going to compare my FP2 model, the model with 2 powers, against a linear relationship. And this time I have 3 degrees of freedom. Why 3 degrees of freedom? My FP2 model used 4 degrees of freedom, 2 powers, but each one of them counts for 2 degrees of freedom. My linear relationship has only 1 degree of freedom, so the difference is 3 degrees of freedom. If this test is not statistically significant, that is, if the change in deviance going from the FP2 model to the linear model using a chi-squared test with 3 degrees of freedom, if that's not significant, I'm done. I have a linear model. Otherwise, I have to turn to test number 3, where I decide whether I need 2 powers or just 1 power. And that's a test, again, comparing the deviances, now a test with 2 degrees of freedom. If this test is not significant, I have my FP1 model. I just need 1 power. If this test is significant, I'm going to use the FP2 model. Well, that was an awful lot of testing. We had 44 models, and then we asked 3 questions, and I was certainly wondering what my alpha level was at the end of this. Ambler and Royston, so there's Royston again, but he's got a new co-author, did some simulations and showed that the algorithm that was on the previous slide is actually got a type 1 error rate that's just a bit smaller than alpha. So he claims to have shown that with all this testing, your overall alpha rate is still 0.05, and you can declare that you've put your variable into the model with an alpha of 0.05. What if you have more than one continuous predictor? Basically, you're in trouble. Basically, if you've got more than one predictor, this type of approach gets ugly really, really quickly. I've got the actual algorithm on the next slide. It comes from the book, which is shown at the bottom here. This book went walking from the U of T library. In other words, somebody decided to add it to their own personal library, so it's not available. So one of our analysts tracked down a copy of the algorithm, and I did reproduce it in case your library is the same and you can't find the book either. It basically uses backward selection to determine which of the continuous covariates is the most significant, and it applies fractional polynomials to that single covariate first. And once it's found the functional form for that single covariate, it then goes looking for the next most significant covariate, continuous covariate. Hopefully some of your covariates may drop out in the process, and it applies fractional polynomials to that second covariate. And then if you have a third continuous covariate, you apply fractional polynomials to that third continuous covariate. And then you cycle back to the top, and you keep cycling through this model of using backward selection and fitting fractional polynomials until you don't exclude any more of your continuous covariates and the functional forms don't change anymore. So you can see that this is going to get really tedious really, really quickly. And you can also understand why I'm just saying that I'm using a lot of hand waving to describe this algorithm, and I have given you the algorithm on the next slide, and I am not going to walk through it. You may count your blessings. So this next cartoon has absolutely nothing to do with fractional polynomials. This just happens to be one of my favorite cartoons. I don't think Sally ever used the word hell in a Real Peanuts cartoon, but I think this is kind of a cute cartoon. Before we go on to use of fractional polynomials in practice, and I have 2 examples. The first one comes from some work that Carl van Walraven did. He's at ICES in Ottawa, and he has come up with a whole bunch of prognostic indices. This particular example is an index which predicts whether somebody is going to die within 30 days after, or have an urgent readmission within 30 days after discharge from a hospital. You can tell from his abstract that he has used that horrible, horrible algorithm that I just showed you, which I said I was not going to go through in detail. Now, he was sensible. He only considered first-degree polynomials. He did not consider second-degree polynomials. So he didn't go completely mad. But you'll see that when I show you the next slide that he did have a lot of work. This is his final risk prediction model. This is not a model that any mother would ever love. You can see that he had a lot of continuous predictors. And if I can find my mouse, the first one was age. And he's got age squared in his model. The second continuous predictor was length of stay, and he's taken the log. The third continuous predictor was the Charlson score, and he's taken the square root, and so on. You can see that for each of the continuous predictors, he's used fractional polynomials to come up with a single power that he applied to that particular predictor. Number of elective admissions in the previous year, power of -1. And he's even got some interactions in here. So this is not a prediction model for the faint of heart. He did not draw a picture of it. What he's done for some of his prediction models is he's got a computer program where you stick in the values for each of the continuous models, and it just spits out your probability of, in this case, your probability of dying. This is not something that a doctor would sit and calculate by hand by any means. Now, the next example that I'm going to show you is a very, very interesting example. There was a single continuous variable. But that single continuous variable was the cumulative duration of exposure to a drug. Now, people got into this study when they started to take a particular medication. And over time, their use of that medication accumulates. So it gets bigger and bigger over time. So cumulative drug use is a time-varying covariate, and it's being used in a survival analysis to look at or to predict time to death. So here we've got a whole bunch of things going on. We've got a survival analysis. We've got an explanatory variable, which is time varying. It's changing over time. And we're going to use fractional polynomials to model the effect of this cumulative use of a drug. So the fractional polynomials are being used to determine which powers to raise this cumulative drug use to. And there are a series of articles. Peter Austin is one of the constants in all of these articles, looking at the effect of cumulative drug use. This article is very important for two reasons. One is that it is a tutorial on the use of fractional polynomials. So even if you have absolutely no interest whatsoever in the effect of cumulative drug use, you will be interested in reading this article because, as I said, it's a very, very readable tutorial on fractional polynomials. And if you are ever interested in looking at the effect of cumulative drug use, you'll want to look at this to see how they did their modeling. So fractional polynomials have pros and cons, just the same as restricted cubic splines. They offer the flexibility, as they claim, a remarkable range of curves can be created. It's straightforward to fit using standard methods. Again, this methodology can be used for any type of outcome, so logistic regression, survival analysis, etc. But it is difficult to present and interpret the results. And once again, a graphical presentation is going to be useful. And I am now going to skip over the questions, although I will allow you to look at my cartoon, because I would like to get through the the remaining part of this of the presentation. Which should I use? RCS, restricted cubic splines, or fractional polynomial? Well, if you knew the nature of your data, in which case you wouldn't have to use either of these methods, you'd know which one would perform better. Overall, in a whole bunch of simulation studies, it appears that fractional polynomials perform better, giving us less bias or more precision than restricted cubic splines, but the differences don't seem to be large. So really, you're free to use whichever one you prefer. The one place where you can't use restricted cubic splines is in Peter Austin's time-dependent covariates in survival analysis, such as his model of cumulative exposure to a drug. And the reason for that is that over time, the values of the exposure to the drug are continually increasing. So you wouldn't know where to put the knots because the range of X values and the value of the percentiles is continually changing over the course of time. So in that case, you do have to use a fractional polynomial. But other than that, you're pretty well welcome to use whichever one you would like to use. I took this this slide in the next one. The reference for this is on the next slide. Obviously, as I said, if you knew what the true association was, you would use it. You wouldn't have to go to the trouble of trying restricted cubic splines or fractional polynomials. This does show you that dichotomization doesn't work very well when your true association is a log. Neither does the linear. Because the log is one of the choices for fractional polynomials, it works perfectly. And this will show you how well the spline does or does not capture a fit when the true fit is a log fit. If your true association is x squared, you probably all know from somewhere very early in your statistics education that dichotomizing or using a linear fit just is not going to work. If your true association is a U-shape, then using a linear association is just going to wipe the relationship out completely. Fractional polynomials, of course, work perfectly because x squared is one of the choices. And the spline fit also works because x to the power 2 is just one form of a cubic with the cubic term set to 0. So the spline will also work. For my messy data set, the one with the huge spike and the huge dip, my best FP2 model had 3 in it twice. It was the 3-3 model. So it contains, I had to add 1 to my x because I had some zeros in there. It contains, my regression model contains x plus 1 to the power 3, and it contains x plus 1 to the power 3 multiplied by the log of x plus 1. That was my best FP2 model. My best FP1 model was just 3, so x plus 1 to the power 3. And my linear model, if I just put x into the model, here's the deviance for that. And the null model, where I drop x out completely, here's the deviance. So my first test is to compare the best FP2 model with the null model. Well, that was highly significant. I had a p-value of 0.001, so I conclude that I do need to have x included in my model. Next, I compare my best FP2 model with the linear model, and that also gave me a highly significant p-value. So I conclude that a linear model is just not going to work. And my final test is, do I need the FP2 model, or can I get away with the FP1 model? And again, I got a highly significant chi-squared test. So no, I am going to have to use my FP2 model. That is the best model, according to the fractional polynomial approach. How well does it fit the data? Not very well at all. This is one case. Of course, you're never going to be modeling anything that looks like this, but this is one case where the cubic spline, with its ability to apply local curves, does much better than the fractional polynomial, which is fitting a smooth curve over the entire range of my data. So in summary, if you fail to include nonlinearity, identify nonlinearity and include it in a model, you can do anything from overestimate or underestimate the power of a relationship to missing a relationship altogether. Models which keep the covariates as continuous are typically better than models which categorize the covariate when it's a continuous covariate. And again, as I said right in the beginning, if the true association is nonlinear and you decide to categorize or assume a linear relationship, you lose power to detect that, in fact, there is a relationship at all. I've shown you two methods, restricted cubic splines and fractional polynomials, which give you a way of testing whether your relationship is nonlinear using standard statistical techniques. And both methods will allow you to model a nonlinear relationship. This reduces the model misspecification. You can read my slides as well as I can. Provides you some insight into what the actual relationship is and gives you great flexibility in what the form of the relationship between the predictor, the continuous predictor, and the outcome are. And both these methods can be used with any type of regression analysis. So having hurried through my last bunch of slides, I'm going to throw open the remaining time to questions. As Anne suggested, I have put up another picture of me, so you can picture me talking. Anybody who is located in my building can take a look at this picture and tell how long ago it was taken. And I'll leave you with one final cartoon while we throw it open to questions. Nothing to do with statistics, just a work from home cartoon. So are there any more questions?
Thanks very much, Ruth, for an excellent presentation. And we do, at least I do, love your cartoons. So, so thank you very much for the comic relief along the way. It's always very useful. So I'm just seeing questions here. Oh, coming through. All right. So first question. Can these methods be applied for extrapolation, and do they perform diagnostics as usual?
The answer to the diagnostics as usual is yes, because you really are just fitting a normal regression. Yes, you've added some pretty peculiar variables to your regression, but aside from that, the diagnostics would be as usual. Extrapolation, you can always extrapolate. It's not a good idea. Yes, of course they'll extrapolate. And of course it's a bad idea. It's a bad idea when you're not using these methods, and it's a bad idea when you are using these methods, because your data doesn't give you any idea what's happening beyond the edges of the data. So if you extrapolate beyond the edges of the data, you're really just guessing that the data are going to continue to behave in the way that they behaved in the range for which you have data. So I would have to say that extrapolating is not a good idea, no matter what method you're using. You may have a different opinion, and you're certainly welcome to it, but that's my opinion.
Okay, I have a question. Can you talk about how to interpret the RCS outputs?
I would interpret it, well, first of all, you have your two questions. Do I need to have this continuous variable in my regression model at all? And if so, is linear fit just as good? After that, I would interpret it using a graph. I would always graph it, because sometimes you'll find, as I said, that although statistically you've got a statistically significant curve, in practicality, that curvature is not useful. There's so little of it that you're going to actually draw back to a linear fit. So in which case I would do a linear fit, in which case, of course, you'd interpret it as a linear fit. But if I have a curve, I would interpret it graphically. This is the shape of my relationship. So unless your graph shows you that you can drop back to a simpler representation, I would say you have to interpret it graphically. I really don't see any other way of interpreting the curve, such as the one that I showed you in Maria's paper, or one that we had recently, which was a U-shaped curve, but it wasn't U-shaped enough to say that we were going to use just use a quadratic. We interpreted it graphically, and we included a graph in the final manuscript, which I can't show you because we haven't published it yet.
Okay, thank you. Are there good tools for doing this work in R?
Almost certainly, because there are good tools for doing everything in R. I'm not an R user. If you don't have a Jiming Feng in your life, I mean, if you have a Jiming Feng in your life, you have good tools because he's written macros. R almost certainly has the ability to do these. I haven't personally checked, but R does everything else, and I see no reason why it wouldn't do this in R. Why it wouldn't allow you to do these methodologies. They're not new. R is fantastic for anything that's new, but it's also fantastic for anything that's been around for a while.
Great, thank you.
So my answer is you're going to have to Google and find out.
Okay. Another question. So this means that we shouldn't interpret the parameter estimates.
I would say you'd have a lot of trouble interpreting the parameter estimates. I have trouble interpreting the parameter estimates for a quadratic. I always have to graph it to see if it's going up or it's going down. But I realize that some people are better at that than I am. So yeah, I would first of all I would have to graph it in order to make a comment about what the parameter estimates are. So your parameter estimates are going to tell you if something's increasing or decreasing, and is it a big parameter, is it a small parameter, is it negative, or is it positive? But after that, I would have to use a graph. If you can interpret it without using a graph, or if you can look at the graph and then put it into English, that's fine, but I would have to draw a graph first.
Okay, thank you very much. I don't see any further questions, although several people have just said how much they enjoyed your presentation and how useful it was. So thank you again, Ruth, for taking the time to do this today and present. I know it's a fair bit of work to put such a presentation together, and all the references that you provided as well will be, I think, very much appreciated by our network of researchers. So thank you so much.
Well, Anne, thank you so much for putting on these presentations.
Great. Well, thank you. And thanks, everyone, for attending. If there are follow-up questions, do send them to me. I can pass them on to Ruth, or you've got Ruth's email here directly. I'm sure she would be happy to follow up on your questions as well.